This video is a continuation of my previous videos, nerds76 and 77. It's about this selective amplifier, which provides an output of about plus 4.5 dBm. And the noise performance, when running it as an amplifier, is minus 142 dBc per hertz when it operates as an amplifier, and the flat noise floor here is minus 172 dBc per hertz. If I disconnect the signal, then the noise is in this line. So 1 dB or 1.5 dB below the observed noise with full signal at 500 Hertz. But at close range there is a big difference. The noise goes up here because the impedance on the emitter of the first amplifier stage is lower. So there is more gain in the grounded base amplifier. What I'm going to do now is to insert a crystal filter using standard HC49U crystals with a Q of up to 100,000 or so, to try to get some attenuation here at starting at 70 Hertz or maybe 100 Hertz, to get a much better noise at 1 kilohertz or so. New crystals are noisy. I have kept these ones in the oven for about 12 hours at a little bit more than 100 degrees centigrade. And then I'm adding more aging using this circuit. 8 dBm, and I turn down the impedance with this transformer first, and then tune for resonance on the crystal, which I see as a minimum on the oscilloscope, and I look at the sideband noise of the signal that I have at the notch. Here is a good crystal. It has been running for several hours now, and this is normal sideband noise that I see in this circuit. I will now put a new crystal here, and first I have to tune on the oscilloscope for the minimum. Something like that. And then I look at the linear screen. This one seems promising. You can see some noise, but this is not very much. So I click on the correlation screen and see what the sideband noise is. So it is significantly higher than what I have seen before, and that is clearly visible here. So I wait for an hour or so. Well, this is just a couple of minutes, and this is typical for quite some time. This is a couple of hours later. I look at the oscilloscope and see if the tuning is still correct. So I move the capacitor to a larger. Well, it seems tuning didn't change this time. Sometimes it does. But as you can see, there is noise from the capacitor when I change it, and it makes a difference here. But I reset and collect data, and standard is to collect at least 100 spectra and then compare with the reference I have here. So it looks, this crystal is now okay. But I wait a little more to see if there is interference bursts. Now I have collected 250 averages and it still looks good. The reference I have is here. So this is actually better. This crystal has been running for more than 1 hour and it's rather noisy, as I can see here. And when I look at the oscilloscope and turn the capacitor, I have increased the capacitance and you can see the frequency has drifted significantly. And I don't think this one will become good even if I wait, so I will just put it on this side in the box where I have crystals that I don't think will be useful. I have disconnected the crystal by cutting this wire, and then I run the amplifier without the influence of a low impedance on the emitter. It will always see a very high impedance, only this 3.3 PF capacitor. What I see then is this curve. That is C, that is phase noise, no crystal but with full signal. And I have also D, which is this curve, that's the amplitude noise. I have removed curves here that were not really relevant. That was when mistuned crystal and different signals input. This curve is when the crystal is tuned precisely to the frequency I'm sending into the unit. That's B. That's phase noise with the crystal at the center. And finally I have this curve, which is the noise when there is no signal present but with the crystal in place. So this is because of the impedance on the emitter being lower than, lower on the crystal resonance, about 50 ohms. In order to get the limits of my test system, I have replaced this amplifier with an BNC female-to-female adapter. And here is what I see. The signal is very noisy above about 30 Hertz. But I do get a measurement below that frequency. Phase noise of my test system is this red curve, and the blue is amplitude noise. And clearly, at very close range, below, let's say, 3 Hertz, my test system is questionable for measurement C. That is phase noise when there is no crystal and with the signal in place. And this is the condition I'm going to study with the extra crystal filter in place. How much higher will the close range noise be when I add a crystal filter? The load on the collector here is very critical. So what I do is to put a 50 ohm load here and then measure the gain from input to output here using the network analyzer. And then I will put the crystal filter here with a 50 ohm output and make sure that I get the same gain on the signal frequency. Then I know that the load will be the same on the transistor. The frequency response is flat, minus 24.8 decibels. Here is a filter with a single crystal that loads the collectors of the transistors properly. I put a 3 turns winding on this ferrite core, then the crystal and the capacitor to ground and one capacitor to the 50 ohm output. And to avoid a very high gain far away from the center of the crystal, I have placed a 180 ohm load at this point where the normal output was before. As expected, the noise level is very high. At 10 Hz, it is minus 110 dB. That is with a 35 dB carrier suppression. 50 Hz, minus 120. With two crystals in parallel and the same number of turns, the Q is significantly lower. So the load on the package of crystals, now two of them, is lower, and there are two crystals to share the power. With these two crystals I have occasional noise bursts, but between them I see minus 113 on 10 Hz, and here minus 122.5 at 50 Hz. Now I have four crystals and still 3 turns on the toroid. Q is now even lower, and of course then the loss through the filter is smaller. Here is the noise performance with 4 crystals. I had to wait about 12 hours to get rid of the noise bursts that are typical for crystals that haven't been aging long enough. Now I see minus 124 dBc at 10 Hz, and at 50 Hz minus 131, and it's still with 35 dB carrier suppression. The noise from the crystals comes here. So they are still too noisy because the curve I have with the crystal, with the high Q crystal, is this line, and I want to be significantly below that to not degrade the close range performance. But the Q of the filter is not very high. I have to go to about 1 kilohertz offset here to get a 5 dB suppression of the noise from here. So I need much higher Q and significantly less noise. So I will try a little bit more to see whether this looks possible or impossible. I have reduced the number of turns here from 3 to 2 on the toroid, on the collector of the transistors, to get the proper load on the collectors. And here is what I see when I tuned the capacitors for the right loading on the collector. And here is the associated transmission through the entire box. Q has doubled to 15,000 from previously it's about 7,000. And the bandwidth at the 3 dB points then is plus minus 350 Hertz or so. So this is a little bit closer when it comes to frequency response, and I will look what happened to the noise. With twice the Q, the power dissipation in the crystals goes up, and I again see this irregular, non-stable noise, sideband noise. And of course, when I look at the evaluation here, the level is very high. It is more above minus 110 at 10 Hertz. So I wait for a while to see whether it improves. A couple of hours later, the instabilities are not quite as strong, but still the noise is not stable and the level is high. 10 Hertz about minus 114. It has been running now for about 30 hours, and I still see these irregular noise bursts from the crystals. So it means power is probably too high now. With twice the Q, twice as much power is circulating in the resonators, I think. So I will reduce the power into the box by 3 decibels to see what happens. Reducing power did not help. I reduced first with 3 dB and then to 6 decibels, and the sideband noise became stronger in both cases. So I made a filter with Q34000 and tested one crystal at a time of those 4 that I had, and one more. They were all manufactured by IQD, and the noise I saw was at 10 Hertz, these levels, minus decibels, and one was really bad, 90, but the best one was 113. I then made a test with crystals from Abracom, and they seem better. So now I'm testing all the crystals I have from Abracom, and here is a typical case, and I can see the noise at 10 Hertz. That's here. I read minus 118, and 50 Hertz, that's here, minus 123. I replaced the crystal with a noisy one. You can see in the waterfall it's much more sideband noise around it, and on the evaluation here about minus 105 dB C per Hertz, and that's with the 35 dB carrier suppression that I'm still using. And I have several crystals from Abracom. I'm testing all of them, and they are different, from about minus 120 down to minus 105. That's 15 decibels. So I will select crystals, the best ones of this kind. Here is the crystal filter I'm using for testing these crystals. Right now, number 248. Input is 0 dBm from a 50 ohm source. And I have tuned this coupling capacitor for a Q of 10,000. And then for each crystal, I fine-tune this capacitor for maximum at the test frequency. And I replaced the crystal here. And this is another bad one. I have tested some of the crystals at reduced power, minus 6 dBm, 10 Hertz, 50 Hertz, and the difference is not big from 0 dBm to minus 6. This one got worse, this one is a little better, this one also. So the good ones may be a little better or the same. And I'm a little bit surprised. I had thought that lower power would make noise much smaller, but that is not what happens. Here is the frequency response. Q is 10,800 and loss is 3 dB, and it is not matched to 50 ohms. I have modified the filter now to get twice the Q. It was 10,800 and now it's 22,000. Numbers is with twice the Q. It seems it reduces performance by 3 dB, 3 decibels more noise, or maybe 4. So that's not too bad. I have put 2 crystals in parallel now, and adjusted Q for about 10,000 or 11,000. These 2 crystals, 258 plus 259, they both give minus 117 dBc per Hertz when measured one by one. So in parallel I expect them to be 3 decibels better, because the noise should be independent between the two noise sources. So what I see is here 10 Hertz minus 120. So there seems to be no magic in that either. A single crystal at minus 117 at 10 Hertz comes here. I have 12 of them, that means 11 dB. That brings me down here. And that would be okay, because the noise from the frequency determining crystal, the 5th overtone one, is here, and I'm well below that. But Q is only 10,000, and that is a bit low, because that gives me 1 kilohertz for the 3 dB points, and that is unsatisfactory. I want to suppress here. At 50 Hertz, I'm here. 125 and 35. And with 10 or 12 of them, I get to minus 171. And it's very close to the curve I want to improve. So I wouldn't improve, I would add nearly 3 dB here and degrade performance. And if I would bring up the Q by a factor of 4, I would lose 6 decibels more. So this idea has failed. I have added an amplifier like this, 6 units containing these components, a transistor BF240 in grounded emitter configuration with current feedback from the collector, a 2:1 turns ratio on a toroid. The impedance here is very low, so I have a 47 ohm resistor to present 50 ohms to what comes after here. Separate voltage dividers for the bases to make noise uncorrelated, and the same for the emitter. And the feed is from the collectors of these transistors, and they are loaded with 36 ohms in the first test I'm doing. A half hour, I have good statistics all the way down to 2.5 Hertz. And here the level I see is minus 116 dB, and with a 45 dB carrier suppression. And I have taken notes on several frequencies, and I will change the scale so I can see also at wide separations. And at 400 Hertz here I see minus 126. I have increased this resistor from 36 to 47 ohms. And that didn't work well. I got 2.3 decibels more gain. That's nice, but noise is 4 decibels worse at 2.5 Hertz, and it's worse all the way. At 400 Hertz, a very small difference, maybe not even significant. But this was not a good idea. I have put back 36 ohms here and added 2 turns on this toroid, so I get 7/5 voltage transformation to get some more gain. That doesn't work well either. A little bit better than increasing the resistor, but still a degradation. So I have tried instead 1 extra turn to get a 6/5 transformation, and that increases the gain from minus 3 dB to minus 1.3 dB. with a rather small loss of performance, maybe 1 decibel or 1.5. And then I have tried to change the output transformation. Transformation was here 2 to 1. I have now made it 5 to 1. And that gives a small loss in the noise performance, but much more gain. So I will go for this solution, at least for a while. I've tried it with different supply voltages. This was 16.87, and that's 18 volts, and 16.15. And the results do not change much. I mean, these numbers may be measurement errors, because at 45 dB carrier attenuation, stability is an issue. There are small drifts in temperature in the room, and things may change just a little. I have set a narrow baseband filter. This one, it's less than 1 Hertz, 0.1 Hertz, so 0.7 Hertz or so. And I have also set a big transform size, n equals 15 here, 32,000. That means that I can do measurements down to fairly close separations. Here I have 1 Hertz, that's here. The imaginary part is fairly strong. That's because the noise of my local oscillators that I'm using for the test system, that is very strong. The local oscillators use ordinary HC49U crystals, fundamentals on 10 megahertz. You saw in the beginning of this video they are noisy, and they have a Q that can be up to about 100,000. But now I am working with a system for a Q of 1 million. So I want to go much closer. Means that I can read down to 1 Hertz, or maybe a little less. Amplitude noise here is almost 10 decibels stronger than the phase noise. This means that setting the phase angle absolutely correctly is very important. Just a small error on the phase means that I get AM noise into the phase noise channel. I have been measuring here for 8 hours, and here is the carrier suppression, and I will fine-tune the phase to see how much it has drifted. And that was a significant difference. So I have lost a little in the performance here. I have set a smaller transform size, now 30. It was 15 before. This makes measurement much faster. And here I can see I have the imaginary part more than 10 dB below the phase noise. So I look at the separation of 10 Hertz. So I look at the separation of 10 Hertz, and here I can read minus 119. Sorry, minus 120, 19.8 or something like that. And then I look at the saved information from the long time measurement at 10 Hertz. That's here. And I have minus 118.9 or something. So the error has been 1 dB, because I get some of this AM noise into the phase noise measurement. The phase noise I see now is this red curve here. And what I had when the crystal was in place is this curve. So all the way up to about here, that is 15 Hertz. The amplifier is perfectly okay. Noise is much lower than the noise from the crystal. But above 30 Hertz, the noise from this amplifier dominates. But the loss isn't very big. I'm losing maybe 4 dB as compared to the level I had here. When I have this noise plus this noise, it will go up to this point, roughly. So I will investigate now when putting back the crystal, because these measurements is with the crystal disconnected. The gain through the wideband input is 6.2 decibels. I have connected the crystal, and now there is a little dip on the wideband input because the crystal is loading a little bit at the resonance. Here is what I see through the crystal. The gain is a little bit low, only 5 dB, so this will not be enough to turn this unit into an oscillator, I think. The Q is 1.1 million. I set the frequency span to 5 Hertz. And this is what you see. And I have the Wenzel oscillator through the wideband input, and I'm sending the signal from the network analyzer through the crystal input. And the Wenzel is attenuated by 60 decibels. So what I see here is the sum of the two signals, and I can see that the 0 is exactly on the peak. I have set the carrier suppression to 30 decibels, and I look at 70 Hertz here, and I see minus 138. And with 30 dB carrier suppression, that is minus 168, which is 70 Hertz, that is here. It is exactly on the line I had for the amplifier without the crystal. And I look at 10 Hertz, that's here, where I put the mouse, and that is minus 127. Plus 30, that becomes minus 157, 150, 2, 4, 6, 7, that's here, on 10 Hertz. That is half a dB above what I measured without this last amplifier stage. So it seems I have a function that is like this red curve, and at this point it should go 3 dB up because they are equal, and then it should follow this curve. So close range noise is still very good, but wide range is good but not extreme. I have been experimenting with the coupling between the first and the second stage and reached some improvement. Here at 2 Hertz I see minus 149, and at 4 Hertz minus 154, and that's very good compared to what I've seen before. But suddenly something happened. This I saved yesterday. Today it looks like this. And this looks like flicker noise. and there is a significant degradation, and it was even worse a little earlier. There are two big electrolytic capacitors in the box, one for the first and one for the second amplifier stage, and I'm not using the third stage now. I have disconnected both of them, and we can see the wide noise is much stronger, but at very close range it seems it is much better now. If I compare with the good result I had before, it looks like this. And I think it is a little bit better now. Here are the big electrolytic capacitors. I had this one disconnected, but now I reconnected it again. And I had this connected, and now I have disconnected it. So I have only a capacitor on the second stage now, 10,000 microfarads. And noise is much lower now. And here, between the white region and this thin line, I had both capacitors. And now it's only on the second stage. And here is what I see. And what I saved before, when it was good, it's this. So, statistics is not good enough yet, but performance is almost restored. So, I have a problem. Here, at this point, I had both capacitors connected, and noise was very low. Now I have discharged the capacitors, and the oscillator or the amplifier is now very noisy. So there is a problem with this, using these big electrolytics in a design like this. As it turns out, the problem is noise from the thermostat on the 16-volt supply line. I have disconnected the thermostat and also disconnected the crystal because it will come on the wrong frequency when not in the right temperature. What I see now is minus 118, which means minus 158 dBc per hertz at 2 hertz. And at 10 hertz here, I see minus 166 dBc per hertz. And when I change the x-axis, then I see minus 173 dBc per hertz at, let's say, 500 hertz. 158 at 2 hertz, that is here. That's where I have the C, which means no crystal, but with the signal. So I have the same that I have seen before. 10 hertz, 166. 10 hertz, 166. That's here. That is 2 decibels less good. And wide range, 5 kilohertz, 173. Curve C. It is here. Minus 172 before. So it is a little bit better on the wide range and not quite as good in the intermediate range. Now, I have made various changes and not optimized. I just found an error that I have corrected. I'm feeding now the thermostat with a separate power supply cable, so it doesn't produce noise anymore on the amplifiers. But the noise, sideband noise level I see is very high. The crystal is connected and at the right frequency because the thermostat is running. Trying to remove the capacitors, the big ones, doesn't make any difference. But I will now disconnect the crystal. And as you can see, the difference is dramatic. It is clearly seen here, but also here. The noise level is below what I see here if I wait for better statistics. But I'm not going to do that because there is obviously something happening when I connect the crystal. Now the crystal is connected again and the noise level is high again. I have been looking carefully for microwave oscillations and other kinds of things that might produce noise, but I haven't found anything like that. I have reduced the power by 10 dB. The crystal is still connected, and the carrier suppression is still 40 decibels. Now I have disconnected the crystal again and still running at 10 decibels lower power. And it's clear from the waterfall here that the sideband noise is much lower. But it will take some time to get a value for how low it might be. Because I can see the red dots here, the imaginary part of the correlation is equally strong as the real part. So I will wait for a while. With a 10 decibel lower signal level, I expect the wideband noise to be degraded by 10 decibels. So now it is minus 162. And I don't remember, but I think minus 173 with the full power. And that single decibel, I don't know where it comes from. At 2 Hertz, I now see minus 147 or something, 2 Hertz here. This is unexpected, because I thought this would be flicker noise from the amplifiers. I will put back the lid on the box. It has been running open, and to see whether that has an effect. Now, with the lid in place, things look a bit different. In the waterfall, I can see that these spurs have disappeared, while there is one weaker here that still survives. And the sideband noise looks different. At 2 Hertz, down here, I see blue and yellow mixed, which means the real part is negative when the curve is blue, and the imaginary part is of the same magnitude. And I see around minus 155 already, and I wait for a while to see where it will go. 3,600 averages, 4 hours and 40 minutes. I cannot see the phase noise closer than about 3 Hertz here, because the imaginary part comes up. It follows at a certain distance from the uncorrelated spectrum up here. As you can see, the distance is about 20 decibels. And the correlation spectrum might not be accurate at much more than that. So I can see that the noise floor is nearly flat at minus 160 dBc per Hertz, and it's likely flat all the way here, because the imaginary part is here, the red dots, and the real part is positive, and it goes down nearly to 0 at this point. So some kind of curve fitting would be like this. And I don't want to wait another 24 hours because this isn't so interesting. What I have found is that the close range noise, the flicker noise, doesn't increase as it looked like before I put the lid on. So it behaves as expected now when I'm running at 10 decibels reduced power level. I was going to replace the crystal, but when I took it out I got this wire in my hand. It has been broken. I will see if I can put it back by soldering. Probably not, but I will make an attempt. This thin silver-plated wire, I think I have soldered it properly on the little tip of the wire from the crystal. So hopefully there is a good electric contact now. To make it mechanically safe, I have put some UV hardening glue here to make the wire strong enough for me to put the crystal back into the oven. The crystal is back in place, and it seems I did find the real error, and it seems okay now. The frequency is not correct because the oven is not warm yet, so I will wait for the frequency of the crystal to have reached the center, and then I will try to measure what is the actual performance now. I have 40 decibels carrier suppression, and I can already see that at 2 Hertz the result is better than minus 151 dBc per Hertz. But I will have to wait for some time now. Now the crystal is back again, and the temperature is stable. Noise at 2 Hertz is in excess of minus 140 dBc per Hertz. 2 Hertz is here, so it's minus 139, roughly. So the crystal works again, but there is noise when I connect it. It's the crystal with another one, and now I see 108 means minus 148 dBc per Hertz at 2 Hertz. So the crystal is noisy. It has flicker noise, the one that I have been using up to now. I will find out what is the actual power dissipation in the crystal before I'm running this too long. Maybe I will destroy it also. I'm running the amplifier at a 6 dB lower input power now, and the noise has degraded a little bit more than 6 decibels at 2 Hertz. So, I don't know really what is behind this, but it seems the phase noise that the crystal produces in the circuit that I have is inversely proportional to the power. Here is the input impedance of the filter. The span is 200 Hertz, and at both ends the impedance is 50.3 ohms resistive and minus 13 or plus 42 milliohms reactive. But 50.3, that's the real part, and that's the significant thing. And on resonance, the resistance is 49.73. Here is the crystal filter. This is 47 ohms in series with 4.7 ohms. And what I observed was 50.3. So there are some losses also in this coil. But the load, the power into the crystal is very small. Under normal operation, means on this input, the impedance I was seeing was 50.3 off resonance and 49.73 on resonance. It means this equivalent diagram, and I can compute the effective resistance of the crystal on the resonance, and that gives me 4.4 kilo ohms. And from that I can compute that the power dissipated in the crystal has to be 4,300 divided by 50 times the power delivered to the 50 ohm resistor. 49.73 or 50.3, approximate that by 50 ohms. It means 73 microwatts, and I don't think that is too much. I'm confused what has happened to the crystal. Now, what I have been doing is I have been injecting 8 dBm on this input, believing that it wouldn't cause more load on the crystal, but I will have to check that. I have placed a 0.68 pF capacitor here on the high impedance side of the crystal, and then I use the oscilloscope high impedance probe to amplify by 20 dB. I have an output on the back side of the oscilloscope, and then I look with the network analyzer. That gives me the voltage here as a function of frequency. And here is what I see on the normal crystal input, the selective input. Now I'm sending the signal into the wideband input, and the voltage on the crystal is much smaller. The only explanation I can come up with is that I may have turned this transistor into an oscillator somehow, and then it could inject power into the crystal that could have damaged it. That's the only idea I can have about this. But the error I find on the crystal, the way it's noisy, is something I never heard of before. I have tuned the crystal carefully to the frequency of the Wenzel oscillator, which I'm driving the unit with through the wideband input. And then I see minus 117 or maybe minus 118. I cannot really say because the imaginary part is the red dots around here. So signal to noise ratio isn't good enough. But the noise is in the order of minus 157 dBc per hertz at a separation of 2 hertz, and that's really very good. Now I look at a little bit wider frequency range, and then you can see I have a maximum here in the phase noise. This looks a little ugly. I have a feeling it is the noise of the Wenzel oscillator, but I have to investigate that. I have added a selective filter on the input signal, and it looks pretty similar. I cannot compare right now, but I will do that a little bit later. I have added a phase modulator, which I feed from this audio generator at 14 Hz. And here is the spectrum I see when I connect my signal source, that is the Wenzel oscillator, followed by the selective amplifier and the 6 dB amplifier, to get the signal into the interferometer. But now I'm sending it directly into the 2-channel receiver to see that the sideband level I have is minus 100 dBc per hertz. The yellow trace, this is the phase modulation, and I click over here to go for amplitude modulation instead. Oh, the thing is very slow. But here is the amplitude trace, and the signal is not present here. It is a pure frequency modulation. And I can see both of them at the same time. If I click once more, so you can see the phase modulation at minus 100 dBc per hertz, and the amplitude is minus 145, and maybe it's just noise. Anyway, this is a nearly perfect frequency modulated signal. I will now send this into the interferometer. Now I'm using the interferometer. It is modulated as before by minus 100 dBc per hertz at 14 hertz offset frequencies. And I'm studying the amplifier that I'm now feeding into the wideband input. So the carrier is suppressed by 40 decibels, but the 15 hertz sidebands are not quite as much suppressed because the crystal attenuates a little on the carrier frequency. But the modulation I have at 14 hertz offset, it is at minus 82, minus 40 means minus 122. And that is 22 dB below what is the modulation on the signal. And this means that the noise humps I was seeing before at minus 161 cannot originate in my signal source. They must come from the amplifier that I am studying. Now I know what the problem is. I had mistuned the filter. I had tuned it with a 8 dBm signal on the narrow input, and then I develop 70 microwatts in the crystal, which shifts the frequency a little bit. So it wasn't properly tuned. Now I have tuned it to be correct on the wideband input. That is how I obtained the good ratio between AM and FM modulation testing with a modulated carrier. And then when I went back to study on the interferometer, the result was very discouraging. So I tried to mistune the filter, and then I came back to this. Now I will tune the filter properly. This is 10 megahertz out from my box, and I'm tuning the capacitor on the crystal for the minimum. That's about here. And here is what I see now. The noise is again very high. There is no problem with the other crystal. It's just very critical how the filter is tuned when measuring the way I'm doing. So I think the amplifier is fine, and the crystal is the source of sideband noise, and probably that will be the case also when running this as an oscillator. Here is my current setup. The Wenzel oscillator, 13 dBm, attenuate by 3 dB to get 10 dBm. Then there is the Selective Amplifier, a similar one to the one I'm just now working with. This one with field effect transistors in it. Output 14 dBm. Then an amplifier, so I get plus 20 dBm. And here is the attenuator. I can set it on 0, and now I will set it on minus 50 as the alternative to get a 50 dB carrier suppression when measuring. Bandpass filter. And here I have a 9 dB very good attenuator from noise properties. and then the unit I'm working with, the device under test. I have added a coupler on this line, which is the sum signal. It is this and that. It makes the sum here and the difference here. And I have a 9 dB coupler to send it into the oscilloscope, where I am usually tuning for the phase and the amplitude. But I added a coupler here to also monitor this signal with the Perseus and Linrod. Here is the screen after 1 hour. At 2 Hz, that's here, I have minus 161 dBc per Hertz. And at 4 Hz, 164.5. And then 170, it is this line, which I reach at about 25 Hz. I will save this to have to compare when I do modifications on the unit. Now there is no crystal connected. I'm just working on the amplifiers. I have disconnected the grounded side of these 2 big electrolytic capacitors to see whether that affects noise. Now that the thermostat has a separate power supply, hopefully they are not needed anymore. Here is what I see with the crystal disconnected. Minus 170 dBc per Hertz is here and comes at about 70 Hertz or so for the phase noise, and minus 160 dBc per Hertz here, something like 2 Hertz. So this is extremely good, but it's only the amplifier. Now I have made measurements through the narrowband input with the crystal working as it is intended to work, and I saved it, and it looks like this, which means I don't need this amplifier at all. The noise I have comes from the crystal, and it's at 5 Hertz, minus 142, and at 10 Hertz, minus 151. So it's reasonably good, but it's not better than the very good oscillators you can find commercially. I have disconnected here and routed the signal 8 dBm that is normally into the device under test directly into my 2-channel receiver. And I have set attenuators here and here to get the proper signal level to not saturate this receiver. But these attenuators are on separate channels, so the noise they produce will not go into the measurement. Here is what I see after 1 minute. And here is what I had in the interferometer. I want to see where to do the measurement best to get the result quickest. So I compare this, which is the sideband noise of my test system, the oscillators, and here the level I want to be able to measure. And I find maybe something like here, the distance is smallest. Or maybe it doesn't matter much. But with a, well, here, 25 Hertz or so, means I can use smaller transforms to collect data quicker. So I reduce from 15 to, let's say, 12. And expand the x-axis. And I will want to look down here somewhere. And now I just have to wait. Because of all the spurs, I increased the transform size to 13, 2 to power 13, and I have waited nearly 32 hours. And I can compare this with what I had when measuring through the amplifier I'm building. That's here. And it's clear that the signal source I have has a lower noise than the output of the amplifier. So this noise comes from the amplifier I am designing. And this is the other unit, clearly better. Here is the noise floor. This has to be a spur that comes in negative. And the imaginary part is down here. So this is probably the noise, because it fits to a line from here up to here. Here I cannot measure. You see the imaginary part is high here. And that's because of the very high noise of the two oscillators in my two-channel system. So if I say something like that, and it seems the noise at the input is not very different from the noise at the output. So at this point I cannot draw any other conclusions than that the input signal is better at wide separations. When I contract the scale, I can see down here that at 200 Hertz the input signal is probably better than 172 minus decibels, and the unit I have is more like minus 170 or minus 171 as it is right now. But the imaginary part is equal to the real part, and the uncorrelated spectrum up here, minus 144, 54, 64, 74, 30 decibels. That is a bit much to trust the correlation spectra, so I cannot really draw any conclusions at this stage. When I look with 2 dB per division, it's more clear that the imaginary part here and here goes something. So only in this region I can see the noise from the input signal, from here to here, roughly. And a problem with my system is the spur, and I have it very much stronger in channel 2 as compared to channel 1. I don't know the origin of it. I will see if I can get rid of it. Here is what I see after 14.5 hours. And I compare with the signal I had at the input. It's more noisy, that's quite clear. The imaginary part is down here, and the real part is at the same level, means I cannot see the noise. But here I could see the noise. Here and here. So the unit I'm testing seems to remove noise. What I see now is better than what I saw here when measuring through the crystal. So it means what I had is here the noise of the input signal, which is not cancelled or attenuated much by the interferometer. That's not surprising. The phase shift is very big so far from the center of this filter, and also the amplitude is attenuated a lot. So I don't have the tools to really know what will happen when I send the signal through this unit. Now I am getting a better result after 14 hours here than what I had with 17 hours when I measured the input signal. The reason is that I have increased the amplitude. On the input I was having a signal level 4 dB below saturation, but I have been more careful. Now it is 0.9 dB below saturation. That's a 3 dB stronger signal, means 3 dB better dynamic range, means 4 times faster to get the same precision. So the dynamic range of the test system is very important, and it's good at wide separations. And I will have a look at what the wide range result is. And it looks like the noise floor is here at minus 169. And that is perfectly in agreement with my expectations. So what I need is a local oscillator, 2 independent local oscillators with a sideband noise that is significantly lower than minus 140 dB. And you can see the ones I'm using now, they are good up to about 50 Hertz. Sorry, they are good from about 50 Hertz and up. I have modified the coupling between the first and the second stage. Like this, here is an inductor of approximately 0.1 microhenry and a capacitor here, and this one is just for the DC supply to the emitters of the transistors. It's easier to see with this equivalent diagram. This is a lossy resonator, LC. 1 ohm, that's the input impedance here at the parallel emitters. So what I see when looking into here is 50 ohms. And that is a suitable load on this secondary winding. I can change the loading on the collector of this transistor by changing the number of turns here. Fewer turns gives more gain because I get more current into this transistor, but it also increases the impedance that this collector is seeing, and thereby it increases the impedance on the emitter, which reduces the Q on the crystal. What will be the best compromise for an oscillator? That will be something to look at when the thing is running as an oscillator. I'm still looking at the output at this point. I have disconnected the second amplifier stage and I'm looking here. I'm using the interferometer with 50 decibels of carrier suppression. So the noise floor at wide range is minus 168. And that is from 50 Hertz approximately and up. There is flicker noise, of course. At 3 Hertz it is at minus 160 dBc per Hertz. This is the phase noise. And here is the amplitude noise, and it's clearly stronger. Amplitude noise and phase noise in the same graph. Here is what my selective amplifier looks like now. I have added an output for a feedback to make it an oscillator. 22 ohms from the emitters through a capacitor, a cross diodes and another capacitor. The output I get now is plus 8 dBm, and that fits to the input here. So with a short cable from here to here, I have an oscillator. There are no big capacitors anymore, since I found the problem was the noise from the thermostat. The thermostat is fed from a separate power supply. So no big capacitors needed, makes the box look much nicer inside. And I don't think I changed much. This resistor is now 270 ohms. It was 430 before. And the number of turns. The output power is plus 18 dBm on the main output, comes from the collectors. I don't have the tools to measure close-range sideband noise at this level, but I have now set up the new oscillator on one axis of this oscilloscope here, and on the other I have the Wenzel oscillator. And on top I have voltmeters to measure the voltage on my unit and on the Wenzel unit here. And there is a frequency tune screw on the box, so I turn that half a turn. And I turn it back. Something like that. So now the frequency is the same, and they are not locked in any way, they are just free running, two oscillators. I can change the supply voltage on the Wenzel unit. I step a little bit on the power supply. There is a time constant because I want to have no noise into the supply voltage connection of the unit. So I'm feeding actually 12.9 volts, and I increase that to let's say 13.1, that's 0.2 volts, and this will slowly go up. And here you can see how fast the frequency is drifting as the supply voltage goes up by 0.2 of a volt. This is less than 1 hertz. What can it take? 5 seconds or so, 0.2 hertz. So I go back and I have to wait for it to stabilize. It takes a long time for the supply voltage of the Wenzel to stabilize because there is a thermostat inside that is fed from the same power supply. And I just have an RC filter with a very big capacitor. So when I change the supply voltage, something changes with the heat dissipation in the unit, and I have to wait for it to become stable again. Now I will change the supply voltage of my home-built oscillator, and it also has a big time constant. So I change the primary supply, which is 25 volts, by half a volt, and you can see the supply voltage goes up and the frequency starts to drift, but not very much. And there is no internal stabilization in the box, it's just not very sensitive to the supply voltage. But how to get out Allen variation or phase noise? I don't know if I have the tools to do that. I may have to build something. I now have 3 good oscillators. The Wenzel and my 2 homemade units with third overtone 10 MHz crystals. One way of trying to get the frequency stability of them is to run them in a waterfall graph. So I did that with the pair sieves, and it is about 4 hours, maybe 5. It's 1 hour per division roughly. So this runs very slow. The resolution, the bin bandwidth, is 1.5 millihertz. The separation, this is the Wenzel, and this is the old, and this is the new of my homemade units. And you can see the separation between them remains constant, and all the variations seem to be the same. So I cannot judge whether one or the other is better or worse because of the instability of the pair sieves. What you see here when it accelerates is it's getting colder now. It's 9:30 now, something like that. I first started with a fairly large separation between the oscillators, about half a hertz, 1, 2, and 3. And you can see that each carrier is surrounded by a spur, about 0.7 hertz on both sides. I don't know the reason for that. Maybe it's the pair sieves, maybe it is Linrad. I will find out later on. I have magnified the graph, and I can measure the separation between my 2 oscillators, and it seems very constant. So the conclusion is they are better stable than plus minus 3 millimeters or so in this graph. And if I compare with the Wenzel here, it's the same. So all 3 are far more stable than the pair sieves. Now I'm using an SDR-IP to receive my 3 oscillators at the same time, and I have locked the unit on one of the oscillators, my latest homemade thing, and therefore it comes as a perfect straight line here. And the noise of the other oscillators, this one is obviously much more noisy than this one. The correlated noise between this and that should be the noise of the one that the unit is locked on. So there is a way from this to compute the noise, but that requires some new software. And there is also a problem. There is noise on this signal as well, as we can see here. And that is related to the phase locking of the SDR-IP. The parameters I'm using, first of all, the sampling rate, the lowest on the SDR-IP is 32 kHz, and the first mix bandwidth reduction is 9, means 512 times. And you see the analog digital speed is 32 kHz. So that gives the sampling rate of the baseband. 62.5 Hz. And then the transform size in the baseband, 15, means 32,768. It gives me a separation between the bins of 1.9 millihertz. I have switched off one of the oscillators, this one. It is my first attempt to make a good oscillator. So the two traces you have left up here, it's the new one and the Wenzel oscillator. I will magnify to look a bit at the details. I have magnified by a factor of 5, which means that each pixel is 0.38 millihertz. And I have a pixel editor, so I can look, when I click on something here, I get the coordinates. And then I move 1385, that's X. And to here, it's about 10 pixels, which could be maybe the 6 dB points or so. So the noise width is something like 2 millihertz. And here, maybe 447 and 4, that's twice as much. So this is very approximate. And here is the spectrum. This is just a single spectrum. And you see there are no spurs anymore, so they were not due to Linrod. That's a problem in the Perseus.